All right, so one of the advantages of being the professor in the class is that you can sometimes choose what to cover and what not to cover. And so I had a lot of fun. I hope you had fun last class when we proved what the Fourier transform was by not doing the contour integral, but rather instead by saying, well, look, we can understand what's going on when C is pure imaginary, and then with accumulation points, analytic continuation, we can get that for the values of C we care about, C real. And that's going to be a key ingredient in our analysis of the central limit theorem. But Cauchy's residue theorem is a beautiful theorem as well, and I feel bad about not showing the residue theorem proof. It's also been a long time since we've done a residue calculation and an integral, so I think it's worth doing the calculation twice. So let's do the Fourier transform of the Gaussian. Okay, so for the Fourier transform of the Gaussian, this is a great way to review the residue calculation. Our density is going to be f of x is 1 over square root of 2 pi e to the negative x squared over 2. This is a normal with mean 0 and variance 1. And so we've talked many times about how to show that this is the correct normalization constant. You can use the polar trick, square the integral. You can convert it to a Gaussian, not to a Gaussian, to a gamma function. And notice that's basically gamma of 1/2. And we have ways to evaluate gamma of 1/2. We want to calculate now the Fourier transform. So we want f hat of c is the integral from minus infinity to infinity of f of x e to the negative 2 pi I x c dx. All right, so how should we calculate this? Well, let's go back to the residue theorem. And we're going to have a contour. Let me see which way I want to do things. I'll do things this way. I hate actually detouring and going down below, but I think this is how I want to do things. Well, I'll do it this way. So unfortunately, this means I'm going to have to choose my contour like this. I'll almost surely have a couple of small sign errors that I hope you can figure out. So we'll go from minus r to r, and then take the limit as we go to infinity. And then over here, I'll have this as r minus, minus it, and over here this will be r plus it. And again, as we've done numerous times, we might want to think, how should r and t depend? Clearly, they're going to be going to infinity, but how is t going to go to infinity relative to r? We can see that as r goes to infinity, we are going to be getting the integral over the real line, except we're going to be running backwards because today I want to go down below. It should be negative I, yes. And that should be also minus t. Okay, so when we're doing contour integrals, we need a function to integrate. So we need a function f of z. Any suggestions for the function f of z? It should reduce to something we know when z is real. So what might be a good thing to try? Any thoughts?
So if we call it our function we want to define now g, then I would define it as g of z was O f of z times e minus 2 pi I z c.
So you would put z in here?
Yeah.
So you would take it like f of z times this? Okay, that's one possibility. The other possibility is to just define it as 1 over square root of 2 pi e to the negative z squared over 2. And now if we take z to be x, if we take z to be a real value, it reduces to this. What this is telling us is maybe we don't want t going to infinity. Maybe we want to keep t fixed. Maybe t does not go to infinity. Any thoughts about what might be a good choice for t? Up to some constants. So So we're trying to get a Fourier transform like this. What might be a good choice? Because over here, z is going to be x plus iy, so z squared would become x squared minus y squared plus 2ixy. This is looking a lot like the function we started with. Any thoughts what we would want y to be? Because y is constant at this height. Y is just equal to t. I'm sorry? Something like c, or pi c, or something along those lines. So maybe what we want to do is now, if we do it just as c like this, you're always going to have to worry about factors of pi and whatnot. So we'll have to figure out later if we really want to do that. Or we can give ourselves a little bit of freedom. Let's do it a times c. And then we'll just figure out what we want to put a to be later so that this will be the Fourier transform. And then if we look at f of x, we get 1 over square root of 2 pi e to the negative x squared over 2. If we look at f of x plus I a c, this is 1 over square root of 2 pi e to the negative. And now we have a x squared over 2. We have an e to the y squared. Okay, y is going to become c squared a squared. So e to the a squared c squared over 2. And then an e to the, we divide by 2, so it'll be ixca. This is looking a lot like our Fourier transform. Remember, c is fixed, so this part over here is just going to come right out of the integral. That looks a lot like our Gaussian factor from before. This looks really close. And in fact, if we think about it, if we're coming down here, c is a negative number. And so I should probably be writing this as minus c to just remind ourselves of how we're doing things. This would then become a minus over here. That would become minus over here, a minus over here. What would we want a to be? What should we take a to be? If we want this to be the Fourier transform. Two pi. So take a to be 2 pi. And so what this is telling us is if we look at a rectangle like this, we can actually calculate the Fourier transform. What's the integral over this rectangle? According to the Cauchy integral theorem, what's the integral over the rectangle? Zero. This function, where is it? E to the negative z squared over 2, there's no poles. So the integral is going to be 0. Wonderful. We need to show that the integral over the two vertical components are negligible. Well, in the vertical components, x is going to be equal to r. And y is going to be at most c. So as r goes to infinity, this part can be growing, but we're going to have an e to the negative x squared. So vertical lines are negligible. It's bounded by e to the negative r squared over 2. We said a was 2 pi, so we'll get 4 pi squared c squared over 2. So we get 2 pi squared c squared. As c is fixed and r goes to infinity, this is small. So we don't have to worry about the contribution from these two parts. So now the integral of this piece plus the integral of this piece is 0. So that means the integral of this piece is the negative of the integral of that piece. Well, since they're the negative of each other, that means I can reverse the order of integration here. And now I'm going in the correct direction. So the two horizontals sum to 0. Flip the top horizontal. And we get the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 dx is equal to this piece, integral from minus infinity to infinity, 1 over square root of 2 pi e to the minus x squared over 2 e to the 2 pi squared c squared e to the negative 2 pi I xc dx. And so we just pull this piece out. What is this integral on the left? 1. We know this integral is 1. So we pulled this piece over to the other side, and we're left with the integral we want. Therefore, the integral from minus infinity to infinity of 1 over square root of 2 pi e to the negative x squared over 2 e to the negative 2 pi I xc dx. This is the Fourier transform at c. It's equal to e to the negative 2 pi squared c squared. Yes?
And when you broke it up into 3 terms on the bottom left, when you were to add one more down?
Right here?
Yeah. Why is that last term, why does it have a minus sign? Where did that come from? The e to the minus.
We wrote z as x minus I xca. So when we square z, we'll get x squared. And then the minus becomes a plus. And then then the I squared becomes a minus for this term. Then we'll have a minus 2x I xca.
But is it e to the minus x? Isn't it e to the minus x squared?
Oh, is there an extra minus sign?
Maybe.
You might be right. There might be an extra minus sign. Yes, you're right. There is an extra minus sign. Okay.
So is that still the Fourier transform?
Okay, so now unfortunately, then we probably should have gone up.
Okay.
So it's actually not going to matter because our Fourier transform, if you notice, is even. If we replace c with minus c, we would be fine. So good catch. We dropped the minus sign. So okay, so we do want to go up top. But this becomes a nice way to calculate Fourier transforms. We can do them by doing contour integrals. And we can convert a lot of these calculations to algebra. Is there a pole? What's really going on is we want to be able to take a Fourier transform and then maybe take the Fourier transform of the Fourier transform. The hope is that if you take the Fourier transform of the Fourier transform, you return back to where you start. That's true if you have an even function. Otherwise, I think you have to do it 4 times. And then the Fourier transform of the Fourier transform of the Fourier transform of the Fourier transform is the original function if everything is well behaved. There's a little sign issue that when you take the Fourier transform twice, you return to the original function but evaluate at the negative of your argument. Okay. So any questions about this? This is the second way to try to do the calculation. And again, it's just trying to show you, now that we have the residue theorem, now that we have all these calculations, what can we do with them? So the next question is we want the moment generating function of the standard normal. So the moment generating function we define as the expected value of e to the tx. This is going to be the integral from minus infinity to infinity of e to the tx 1 over square root of 2 pi e to the negative x squared over 2 dx. When you see this, what's your first thought as to how to approach this, to do this integral? So what's your thought as to how to evaluate this integral?
Combine terms and try to complete this.
Combine terms and try to complete the square. Completing the square is one of our most important techniques. So this goes all the way back to the quadratic formula from 7th grade plus or minus 2 grades, depending on how advanced you were back then. This is a great use of completing the square. So this is the same as 1 over square root of 2 pi, integral from minus infinity to infinity, e to the negative 1/2 will have x squared. When we bring the tx inside, we multiply by 2 over 2, so it'll be a minus 2tx. Let me make sure, because I've already made one minus sign mistake today. Minus times minus is plus, good, the 2's cancel, good. So now what would I want to add here? So if I want to complete the square, what should I add?
T squared.
Yeah, add t squared, and then subtract t squared. And what you'll see is we can pull out this t squared over here. We'll have a minus, so we get an e to the t squared over 2, 1 over square root of 2 pi, the integral from minus infinity to infinity of e to the negative x minus t squared over 2 dx. This is just a normal. What's the mean of this normal? T. We've just shifted everything down by t. The variance is still 1. If you want, you could do a change of variables. You could let u equal x minus t, and then this would just reduce to the standard integral we've seen numerous times. What does this integral equal? 1. We're integrating a probability distribution. You could also notice u equal x minus t. That would also work. So we get that the moment generating function of the normal is just e to the t squared over 2. And this converges for all t. So it is not always the case that moment generating functions converge. Fortunately for us, the normal converges. Instead of using the moment generating function, sometimes people use the characteristic function. And this is defined as basically the moment generating function at it. And the advantage of putting an I here is that it's the Fourier transform, up to pronunciation. So different people define the Fourier transform in slightly different ways. This way it doesn't have the 2 pi's, it doesn't have the minus sign. That's not a big deal. It just rescales t by a multiplicative constant, like a negative 2 pi. The advantage of the characteristic function is it always exists. The moment generating function to me is a little bit more conceptually nice. When I think of probability distributions, I think of moments. And if I understand the moments, I think I should understand the distribution. Okay. Any question about what we've done so far? Is the battery no? No, it's looking it's not interesting. Okay. All right. So what we want to do now is we want to sketch a proof of the central limit theorem and just see how everything comes into play. And then there's going to be some complex analysis difficulties in the convergence. And that's where our tools are going to help us. And we'll be able to prove everything. We're going to need one small result from Fourier transform theory, which if there's interest, I'm happy to prove that later. If not, I'll just say this is the final nail you need in the coffin. But I want to give you a sense of why knowing integral moments is not enough. Because when you take a first course in probability, you see moments all the time. There's a huge focus on the first moment, the mean, the second moment, which gives you the variance. These are the key ones. The other moments help tell you the shape. You might hear words like skewness and kurtosis. But it turns out you can have two probability distributions where the moments agree, but they're different. And we saw an example of that last time. All right, so here is a proof of the central limit theorem. So for us, x1 through xn are independent, identically distributed random variables, finite moments, and in fact, the moment generating function of t is the moment generating function of any one of them, converges for all t less than some positive delta. Okay? We're going to let Zn be x1 plus xn minus n times the mean divided by sigma square root of n, where mu is the mean of the x's and sigma squared is the variance of the x's. So what we're doing here is we're normalizing, or we're standardizing a quantity to have mean 0, variance 1. So the expected value of Zn is 0. The variance of Zn equals 1. This is basically the nicest transformation I can do. I can always adjust to have my mean be 0 if it's finite. Can I also adjust to have the variance be 0? Typically, no. There's only one way I can do that. The only way I can adjust to have mean 0 and variance 0 is if I have perfect information as to where the particle is. With 100% certainty, it's at this point. Then it's no longer really a probability distribution, it's a point mass. Okay? So in general, we are not going to be able to make both of these 0. Well, if this can't be 0, you might as well rescale to have it be 1. 1's a really good value for things to have. And what we want to do now is we want to calculate what's going on. So we want to look at the moment generating function. And so the claim, which is the central limit theorem, is that Zn goes to z, which is normal 0, 1, as n goes to infinity. I'm going to be a little vague on exactly what do I mean by this convergence. What we're going to show is the moment generating function of Zn of t converges to the moment generating function of the standard normal. And then what you hope this means is that the probability density of Zn, in some sense, goes to the density of the standard normal. That if the moment generating functions are converging, the density should be converging as well. This is where there's some technical difficulties. And the nicer things you assume about your underlying distributions, the easier this last step is. But what we will do is we'll see at least enough to get a sense of how complex analysis comes to the rescue and how knowing just the integral moments is not enough. Okay? All right. So let's start doing the proof. So we want to calculate the moment generating function of Zn of t. And this is going to be the moment generating function of x1 plus xn minus n times mu over sigma square root of n of t. Okay? So we need a couple of facts. The first is that if you have two independent random variables, if independent, the moment generating function of a sum is the product of the moment generating functions. There's a lot of ways to prove this. Probably the simplest is the moment generating function of the sum. By definition, it's the expected value of e to the t x1 plus x2. How should I view this product? I'm sorry, how should I view this sum? I think I just gave it away. I should view it as a product. So it's e to the t x1, e to the t x2. You can put an asterisk. This is one of the few times in life when you do not take a logarithm. Because these are independent, when I take the expected value, I'm integrating over x1, I'm integrating over x2, I can just have this part against x1, this part against x2. The expected value of a product of independent random variables is the product of the expected values. And so you'll just get the expected value of et x1, expected value of et x2. And that's the moment generating function of the first and the moment generating function of the second. And that will finish the proof. Okay, so we're comfortable that the moment generating function of a sum is the product of the moment generating functions if independent. If I have 3 terms, I just proceed by grouping. I group x1 and x2 together as my first thing. So x1 plus x2 plus x3 would be the moment generating function of x1 plus x2 times the moment generating function of x3, and then I expand that out. So any finite n, I can expand like this. The next fact we need is that the moment generating function of alpha x plus beta of t is e to the beta t, the moment generating function of x at alpha t. How do you think we prove this? How do you think we should prove that? Yes, same way. We don't know that many things. Go back to the definition. The moment generating function of alpha x plus beta of t is the expected value of e to the t alpha x plus beta. And now we expand this exactly as before. It's the expected value of e to the t alpha x e to the t beta. Does this have any x dependence? We can pull this out. And this looks like the moment generating function of x, but not evaluated at t, evaluated at t times alpha. And so when we pull it out, we'll get e to the t beta and the moment generating function of x at alpha of t. So these are very straightforward facts about moment generating functions. This is one of the reasons why we like moment generating functions so much, is that they are beautifully suited to probability. It's very hard to work with densities. It's very hard to work with the convolutions. What moment generating functions are essentially doing is they're converting convolution to multiplication. We can deal with multiplication. Okay? And now, once we know multiplication, we can then do the analysis. Okay. If instead of using the moment generating function, if we use the characteristic function, would this still be true? Would these results still hold if we used characteristic functions? So what's the relation between the moment generating function and the characteristic function? So how are they related?
Yeah, it should help.
Yeah.
Just use IT.
Yeah, all we do is replace every t with an it. No difference. The proofs are all the same. So instead of working with moment generating functions, if you want to work with characteristic functions and actually have objects that exist, not a problem. Okay. So now we can start proving the central limit theorem. And so we're going to use our facts. Okay, so let's return to proof of the central limit theorem. So we have the moment generating function of x1 plus xn divided by sigma root n. Now we have minus n mu over sigma root n. So that should be minus mu square root of n over sigma at t. Right? I've done the division correctly, I hope. Well, now we use our second fact. This is going to be our alpha x, and this is going to be our beta. So this is going to become e to the negative mu square root of n over sigma t, the moment generating function of x1 plus xn, my random variable. And what's my alpha equal to here? Xn, 1 over sigma root n. So let's try to think about what's going on. As n gets very, very large, we're evaluating the moment generating function essentially at what point? 0. If you ever have to choose a point to evaluate the moment generating function, if you could choose any point, where would you choose to evaluate it? 0. The moment generating function of x at 0 is just the expected value of e to the 0x. What's this expectation? 1. Now, this is not evaluating it at 0, but it's evaluating it close to 0. So this should be very close to 1. Now we're going to use our first fact. The moment generating function of a sum is is the product of the moment generating functions. As the variables are independent and identically distributed, I'm going to get the same moment generating function just n times. So this becomes e to the negative mu square root of n over sigma t, and then just my moment generating function to the t over sigma root n to the nth power. So this is going to be very close to 1, but we're raising it to a huge power. So because we're raising it to a huge power, small deviations from 1 could be magnified. We can Taylor expand this. And if we Taylor expand this, well, once we get up to a cubic term, we'll have a t cubed over sigma cubed n to the 3/2. I'm not too worried now at that point, because I'm only raising it to the nth power. So probably a cubic term would be more than enough. So there's lots of ways to go about this. Any thoughts as to how we should continue the analysis? What should we do looking at this? Hint, if Professor Miller, i.e. myself, ever asks you what should you do, what should your first thought be? Not Taylor expand.
Induction.
Not induction. Take the logarithm, right? When in doubt, take the logarithm. Why do you take logarithms? What do logarithms do? They turn products into sums. I wish I could turn lead into gold. I can't. But I can turn products into sums. For mathematicians, it's almost as good. Not quite, but almost. Do we have any products here? Hell yes. Technical term. We have this to the nth power. You've got to be extremely careful when you have things raised to a power. If I start Taylor expanding this, I might be a little bit worried because I have something to the nth power, and then when I expand, I've got to worry about combining all the different things. You could do it, but I think it's a little bit cleaner to take the logarithm first. And we'll get the log of m zn of t. And the other thing is this is beautifully set up for log, right? This piece here is going to become a negative mu square root of n over sigma t plus n times the log of mx of t over sigma square root of n. Okay. Can I erase this stuff over here? Do we need this anymore? Okay. So now let's look at that last factor. We have n log mx of t over sigma root n. So we know mx of t, we talked about this before, it's the moment generating function. It's 1 plus the mean times t plus the second moment over 2 factorial t squared plus something of size t cubed. So we are going to be essentially doing a Taylor expansion. If I now plug in not t, but t over sigma root n, we get 1 plus mu t over sigma root n plus the second moment. Now, we actually use the prime to denote that it's a non-centered second moment, over 2 t squared over sigma squared n plus something of size 1 over n to the 3/2. So as we start putting in the higher terms, it's going to be very negligible. Why is this good? I've got the log of 1 plus something small. We can expand. The log of 1 minus u is negative u. Well, actually, we got a plus. A log of 1 plus is u minus u squared over 2 plus u cubed over 3 minus yada, yada, yada. Let's think of how many terms we actually need. You might be tempted to say, well, look, I only need one term because this is being divided by square root of n. This is already small. Why do I claim we need to at least consider this term?
There's an n.
Yeah, there's an n outside, which is huge. This is the best way to minimize your chance of making a mistake with high powers, is to take logarithms, Taylor expand, and then just keep that high exponent over here. The n times the 1 over square root of n, that's going to give us a square root of n up top. Fortunately, that's going to be perfectly balanced by the negative mu square root of n over sigma on the other side. What about the next term? Do we need to keep this term? Do we need to keep this term? When we multiply by n, is it sizable? Well, n times this is going to be of size mu 2 prime t squared over 2 sigma squared. That's of size 1. When we multiply this by n, as n goes to infinity, does this go to 0? No, we have to worry and keep this term. What about the next term here? When n hits this, what do we get? What size is that term going to be when it's hit by n? 1 over radical n, negligible. Now when we look at the u squared, when you look at the u squared term, this whole mess here is our u. Over here, do we have to worry about this as a u squared? Mu squared, t squared, sigma squared, n, crap. When we multiply this by n, it's of size 1. We have to worry about this part in the u squared term. Do we have to worry about this in the u squared term? Well, we're now squaring the whole thing, so we could have this times this. Well, if you have this times this, what's the order of that going to be? It'll be a 1 over n to the 3/2. We don't have to worry about it. When this hits itself, it's going to be a 1 over n squared. We don't have to worry about it. When anything hits the n to the 3/2, we don't have to worry about it. So in the u squared term, we only have to worry about this. In the u term, we have to worry about the first two. What about the u cubed term? Do we have to worry about anything? No. And then you can basically just show over here, in fact, we can just write this as it's plus some error of size u cubed. Use the geometric series to bound everything that comes behind. We don't have to worry about anything here. So we get n log of mx of t over sigma root n is going to be u. So it's going to be mu t over sigma root n plus mu 2 prime t squared over 2 sigma squared n. I'll just write the big arrow term at the very end. Now we have a minus u squared. The only thing that survives is this part over here over 2. So we get a minus mu squared t squared over 2 sigma squared n plus an order 1 over, okay, I made a small mistake, 1 over root n. What's the mistake I've made? I made a small algebra mistake. Not a big deal. Easily fixed.
We have n.
Yeah, I forgot to multiply through by n on this side. So when I multiply by n, the square root of n down below moves upstairs, moving on up, as the Jeffersons would say. The n down here is gone. The n down here is gone. And I had done the algebra correctly over there. So this is what n log of mx of t over square root of n is going to look like. Okay, we no longer need this stuff over through here. We are almost done. We will definitely finish today. So now we get the log of mzn of t. So we had the negative mu square root of n t over sigma. Now we have to add in the n log m. So we get a mu square root of n t over sigma. Isn't life wonderful? The term that blows up as n goes to infinity perfectly cancels. The next piece that we get will be a mu2 prime. We have t squared, so minus mu squared. I'm just going to factor a little bit, over 2 sigma squared t squared plus order 1 over square root of n. Now, mu2 prime is the expected value of x squared. Mu is the expected value of x. So mu2 prime minus mu squared is the expected value of x squared minus the expected value of x. If you do a little bit of algebra, this is the same as the expected value of x minus mu squared. Here, yes, that should be squared. And what is this quantity? That's just our sigma squared. So this quantity over here is just t squared over 2. We are really close now. So we now get that the log of mzn of t is equal to t squared over 2 plus something of size 1 over square root of n. All right, now what do we do? Exponentiate. You take a logarithm, but then at the end of the day, you actually exponentiate to get back to the quantity you want. So that means mzn of t is e to the t squared over 2 plus big O of 1 over square root of n. That's e to the t squared over 2, e to the big O 1 over square root of n. But you might recognize e to the t squared over 2. What is e to the t squared over 2? It's the moment generating function of the normal. So we get the moment generating function of Zn is the moment generating function of the normal times 1 over square root of e to the 1 over square root of n, or something of that order. So as n goes to infinity, the moment generating function of Zn of t goes to the moment generating function of the normal. And in fact, we even have control over the rate of convergence. The central limit theorem is essentially the fact that you can now replace the m's with the densities, at least if the random variables are sufficiently nice. That's what we'll get to in Monday's lecture. That's where we'll start to use the complex analysis. We still have a few minutes, so I can hop on some points. This is miraculous. This is one of the big results in all of mathematics. You don't get a name like central for nothing. Is there anything that's surprising about this result?
It doesn't matter what your initial distribution is.
Yeah, that seems a little surprising. That I can take essentially any nice random variable and just keep adding copies. What is going on? Well, what's going on is if you look at the moment generating function, it's 1 plus the mean plus the second moment of 2 factorial t squared. And now this is where the higher order terms come in. Mu 3 prime over 3 factorial t cubed plus dot dot dot. The higher moments that control the shape of the distribution don't surface until the third order. When we do all of our analysis, it's only things up to second order that contribute in the end. This is why the shape does not matter. Because if your distribution is nice, you can always normalize to mean 0 and variance 1. So the shape of the distribution should not emerge until the third moment or the fourth moment if it's a symmetric distribution. where does the shape of the distribution come into play? It comes into play in here, in the error term, in how quickly normal sets in. Which do you think will converge to the normal faster? A symmetric distribution about the mean, or a non-symmetric distribution?
Symmetric.
Symmetric. If you have, let's say, a distribution that's symmetric about 0, the third term will be 0, and you will actually, maybe things won't kick in until the fourth. And so you can actually look at, see what happens when you add uniforms to uniforms versus exponentials. And you can see how that symmetry comes into play. So there's a lot of great stuff going on here in this calculation. This is the moment generating function. We get to use our logarithms. Now, we're doing everything in terms of the moment generating function. Could I have replaced m with phi? Could I do a search and replace? Would any of these arguments really have changed if we used a phi rather than an m? No. All that we're doing is we're evaluating things that are imaginary. We've taken complex analysis. So the real difficulty is going from this line to a statement about the densities. And there's got to be something non-trivial going on, because we saw an example of two distributions that have the same moments, but do not have the same density. What do you think must be going on? Bless you. Something should be breaking down, right? There's got to be some issue.
Taylor series, not analytic.
Ah, maybe the Taylor series is not analytic. Maybe the Taylor series doesn't converge. And that could be the problem. So we had a problem where we were looking at these densities, the densities of the log normal. Look and see what the moment generating function is there. See if they converge. What we're going to see is, we'll need to assume one small result from Fourier analysis, but we will then look at, on Monday, finishing the proof and seeing how points of accumulation help us go from, if a sequence of moments accumulate, then the densities must be equal. It's all going to come down to inverting the Fourier transform. And so my plan is not to prove that, because nobody really, when I asked what do you want to see this semester, nobody said they really want to see Fourier analysis. So I'm not going to plan on that. But if people change their mind now that we've done all this, I'm happy to do that. I was thinking of going from this into Laplace transform, Fourier transform, Mellin transform. What we have is we have these integral operators that's underlying this whole theory. And talk a little bit about how we can use these to solve differential equations. So as a nice exercise, again, I'm not going to assign it formally. We calculated, or we got to the point where I left it as a calculation for you to determine the moments of the log normal distribution. So my question to you is, does the moment generating function of the log normal converge for any values of t other than 0? And that's a really good thing to think about. Okay, any questions on where we are? And I apologize, we ended half a minute early.